Hey guys, so we just finished talking about normal distributions. Let's go ahead and jump into sampling distributions. So in particular for means, as of now, the normal distributions we've worked with only deal with population of individual observations. So for example, what's the probability of randomly selecting an individual who is taller than 6'3", right? And so a more accurate measure to use is the sample average or sample mean, since they're less varied than the individual observations. And so basically, if I had just picked a random person, it's kind of likely that maybe they could be 6'3", but that's not the average height, right? So our average height, it's kind of unlikely that they'd be 6'3", and our average height may be, like 6 feet, 5'9", I don't know, whatever the case may be. Basically what happens is that once we take an average, and we're talking about a sample size greater than just an individual person, what happens is that the measure spread gets smaller and smaller because we get closer and closer, more accurate measure of the average. Does that make sense? So kind of the normal distribution gets skinnier and skinnier and skinnier, so that it looks very clustered around the average, around the mean. So to determine whether you're working with a normal or sampling distribution is if they mention is there's any mention of a sample. So n equals some number. So if they ever mention a sample, automatically you're working with a sampling distribution. Because again, the normal distribution is based off a population of individual observations, so not any samples. So just like the normal distribution had a mean and measure of spread, so does a sampling distribution. The measure of spread, however, for the sampling distribution isn't just the standard deviation anymore. So it's a little different. It's kind of like an augmented standard deviation, and it's called the standard error. So for individual observations, the standard deviation is the measure of spread. When we're talking about samples, you call it the standard error. And the reason being is that the standard deviation represents just something in itself. So it's actually just one particular, for example, we calculated it before, right? So there's a formula to it and everything like that. Standard error is something a little different. It's still a measure of spread, but it's a measure of spread particularly for sampling distributions. So let's go ahead and look at some variables that we're going to be seeing. So we have our handy dandy normal distribution, right? And sampling is just a skinnier version of it. I'm just going to keep the same drawing there just because we've been working with it and it has a lot of space to write in it. So the mean of the sample means is just the mean of the population, so that doesn't change. And the reason for that is because it's just the midpoint. It's like saying the midpoint of the midpoint. If it's the midpoint, that's that number there. It doesn't get any more exact than that. So the mean of the sample means is just the mean of the population in general. And then we also have the standard error. So you see a little sigma, so it kind of tells you it's like a measure of spread, but particularly for sample means. So that's why you have the x bar there. And that's standard deviation divided by square root of n, where n is our sample size, right? And so again, we kind of see mathematically also that the measure of spread, that standard error, as we increase the sample size, right? So as n goes up, what happens to the standard error? It goes down, right? Does that make sense? So bigger sample size, the more accurate we get, and the skinnier, the less spread out this sampling distribution gets. And then we also have our distribution here. So let's go ahead and just put in everything. So we have the mean of the sample means, and these are going to be a bunch of x bars. And so instead of x's, like individual observations we were working with before, we're talking about sample averages now. So we're going to have, z-scores for averages and things like that. And then we have the standard error. So that's basically how it works. We're going to dive into the z-score and probabilities and all that stuff a little later, but I just want to establish this next concept first. It's the central limit theorem. So we can only assume that the sample would look normal if the population was normal, right? So for example, IQ scores, they're normal. So we would expect any sample that I draw from that to also be normal. However, the central limit theorem states that regardless of the shape of the population, if the sample size is large enough, the sampling distribution is approximately normal. So let's assume that here's a sample size of 1, 5, 10, and 30 plus, so 30 or more. So here we have a normal population, right? Because the distribution itself still looks normal. It's a little kind of short and fat, but that's basically what it looks like. So that's normal distribution, and that's for the population. The reason why I know it's for the population is because it's based on a sample size of 1, right? So we're talking about individuals, just like we were working with before. So an individual who's taller than 6'3". So we're working with one particular sample size, and here we see that it's normal. But what happens as we increase the sample size? You see it's getting skinnier and skinnier, right? So basically, again, that has to do with the idea that when we're talking about average, it's not as varied as any individual object being pulled out of a hat. And the reason for that is because the higher numbers we have, the closer to the average we should be. So our numbers aren't as varied anymore, the higher the sample size. So that's what happens basically from an individual the population, when we're talking about individual observations, and as we move to bigger and bigger sample sizes. Now next, here we have, what would this distribution be? Skewed to the left, right, or normal? Or symmetric, I guess, technically. It's skewed to the right. So this is kind of going back in the day when we were talking about distributions and their shapes and all that good stuff. So it's skewed to the right because basically most of our data is on the left, so clustered around the left, but then we have random outliers on the right side. Does that make sense? So here now we get a sample size of 1, that's the population, and then as we increase the sample size, we see that the sampling distribution looks more and more normal. And so the basic rule for the central limit theorem is that regardless of the shape of the population, as long as you have a sample size that's greater than or equal to 30, you're good to go and you can assume that it's normal. Now the whole reason for this and why it's so important is because with this assumption we can go ahead and start using the z-score and the z-table to help us find probabilities associated with finding, for example, a sample mean of people being taller than 6'3", for example. So we can find z-scores, we can find probabilities, and it basically sets us up for the rest of the lesson, so that we understand that, you know, now that it's sample size greater than or equal to 30, we're good to go and we can work with the z-table. So that's about it for sampling distributions in general, kind of, and now we're going to really focus on the sample mean.